Hello, everyone. Welcome to the last talk of this year's KVM forum. I hope you are not too tired, and thank you for everybody who stayed for that long. So I'm trying to talk a bit about CPU models, and basically, this is supposed to be more like a problem statement kind of talk. I don't have really any solutions, and anybody who has looked into the problem of CPU models won't be surprised, I guess. So what do I want to talk about right now? So what's the actual state, which is, confusing? And what do we actually need? So what has prompted this is basically everybody wants CPU models on all architectures, and on ARM it's a bit difficult. And and the last one is I'm trying to come up with some ideas of what we actually want to do. But I don't have any solutions, and what I really want is that we can discuss things and maybe rule out stuff that won't work at all, and maybe just start the discussion, which can, of course, continue and will continue, I guess, later on. So where are we right now? So if we look at the different accelerators for TCG, we basically have named CPU models. You can say, hey, I want a Cortex whatever, I want a Neoverse, and there are various types available. And if you just start your QEMU with the CPU model, you will end with something that is reasonably accurate to the model you actually specified. The other option is the max CPU model, where you just go ahead and let's just emulate everything that exists and just give it a go with everything that's new and cool and so on. For KVM, it's a bit more difficult. We also have a max CPU model, which is basically the host CPU model. So basically we look what does the host do, and we try to enable this if we have the code available and we know about the features and so on and so on. We also have named CPU models, which are not that useful because you would need a host that is actually matching whatever is in the model 100%. And good luck finding a CPU which actually matches. We have also a bunch of CPU properties which you can explicitly specify when you are trying to initialize your CPU. There are various categories. So you have some properties that match one-on-one to a ARM CPU feature. This is very obvious what this does. Then you have some TCG specific stuff, and then you have some KVM specific stuff. This is mostly, at least in the KVM case, it has mostly been introduced to be able to deal with older versions of KVM. And what do we actually need? Because we don't currently have really much on the ARM side. If you compare this to other architectures, they have a much richer feature set where you can switch, for example, CPU properties on off. You have something like CPU model expansion, which also exists, of course, for ARM because it's a generic feature, but it's not that useful. What I think we really need is basically we are defining a CPU. If we have this, we specify I want a CPU with this and that, and then we want to have a reproducible thing. So if you have a newer QEMU, if we have a slightly different setup, we still want to get the same CPU and not something which is similar just because we end up with a newer CPU, with a newer code level, and then you just have new stuff there. And then you are wondering suddenly, why does your guest see features that didn't exist before, or why does it behave differently? I don't think anybody desires that. We also have new features coming up all the time. We also want to be able to just use them quite easily and not to need to write a lot of boilerplate code just to get all of this going, especially if you consider higher level administration interfaces like libvirt. Then we don't want different accelerators to be completely different. So if we have a command line that works with KVM, it shouldn't be something completely different on TCG or on any other accelerator we might want to use. And last but not least, a management interface like libvirt also needs to be able to actually find out what is supported on the platform. So it can say, okay, I'm spinning up a VM, and this is what my system currently supports, and not just try it, and if it doesn't work, then we'll just try again. That's not a good use case. Compatibility handling is probably one of the more fun parts, especially if you consider live migration. If sometimes you will need to migrate a system from an older version to a newer version, and you don't want to see any change in the guest for those migrations. And for this, we really need to have something that is actually reproducible. So like say, hey, we want a CPU with those and those features, and then we have a newer version and have the same CPU, and it just does not look any different in the end. And yeah, the other thing we use for compatibility in QEMU is, of course, compat machines, and those compat machines might have some intersection there. I've seen it on other architectures like SV90. They have intersections with whatever, like you have the compat machine and then you are doing some feature bit fiddling for the CPU so that we end up with the same thing in the end. And we might want something similar on ARM as well. And but what I think we need to do, we just need to limit ourselves. If we look at the ARM ecosystem, the CPUs that are available are just really, really different. You cannot just pick a random CPU and then expect to be able to migrate to something which is completely different. This won't work at all. You'll just go crazy if you try to do that. And that's also a difference like to other architectures. So x86 is, yeah, it's also quite heterogeneous. SV90 is better, but even on SV90, we have variability, and ARM is just far out to the right if you look at it like that. And we also, if we want to have something cross hypervisor, we also need to consider what the accelerators need to do. TCG is simple because TCG, we control what we actually do because we are doing it all ourselves. But for KVM, we also need some support in the kernel, like, hey, we don't want this feature bit. And I mean, there's a patch set currently on the list, which is trying to make this accessible to user space so that we actually can configure some stuff. And this is going in the right direction, I guess. So this is something we will definitely need in the future. And I want, maybe this is probably the most horrible thing. I see a lot of nodding here. We do not really, we have errata all the time. We have changes all the time, which are not really architecture-wise. We have some really, we could have some CPUs which look the same on the surface, but in the end, they are behaving differently. And this is probably the worst nightmare. And there's also the question, what should TCG do? Should TCG just ignore all of that stuff and say, okay, we are just sane. We are TCG, so we can do sane stuff and don't need to worry about what real hardware is doing. That's probably the easier approach, but yeah. And how can we actually move forward here? So the problem is, how do we actually name our CPU models? If we agree that somebody firing up their system, they want a CPU with a certain feature set. In many cases, they know, okay, I am running on a whatever, Cortex, whatever, and I want a Cortex, whatever. And if I'm using TCG, I'm just doing that. I'm saying, hey, give me that Cortex, whatever. This is the problem with this is it's not easy. It's not really scalable into the future, and it's also not really scalable across the many versions of CPUs that exist, and the many CPU vendors that exist, and the many boards where people put CPUs in, and all that kind of stuff. It would mean we would need to patch QEMU for every new CPU that comes along, and this does not scale at all. Using architecture revisions would be another options like, hey, I want an 8.6 CPU with the following optional features. This fails if we are trying to consider KVM because we cannot really reliably figure out what is the CPU. We might not know what architecture level is this actually. We might guess, but we may be completely wrong if everything comes just in the right places. Well, I think we need to go with the Frankenmonster CPU. It's basically build your own. It might look like a real CPU that actually exists, but we will just try to figure out on KVM basically what does the host do. Build a CPU model that basically is the intersection of what the host does, what our software does, and assign it a UID. And then if we know how to construct it, we can also construct it, for example, on the destination host if we are doing migration and build something there. And I mean, for TCG, you can also go ahead and say, oh, I want this really weird CPU that doesn't exist in the wild, but I'm just building it anyway and just assign a UID, and there you have with your very weird CPU. The other thing is currently there's a lot of properties that are not configurable from the QEMU command line. We have set, I think it's like 10 kinds of properties where we can actually configure something, and more if you have, for example, different vector lengths. But it's really not much. If you look at typical POC CPU info in Linux, you see many more variations of features, especially if you look at one of the newer hosts. They have a real zoo of features they expose, and if it shows up in POC CPU info, we know that the guest knows about it. So if we want to ensure compatibility, we need to be able to actually configure it so that the guest isn't suddenly surprised that something is there but that wasn't there, or the other way around, which is probably worse. So basically, as I wrote here, if it's something guest supportable that may differ, we must be able to actually configure it, or we cannot support the compatibility between those two CPUs. Yeah, and I listed more of this, and it's basically, if you look at it, you are going crazy. Just look at the features that are supported in ARM revisions, that features that are added, the combinations that might be possible in the wild. Yeah, it means we really need to limit ourselves, because otherwise it is just a support nightmare. Then we have obviously the big difference between TCG, where we are in control. Basically, the CPU does what we have programmed it to do. And for KVM, we have the real CPU on the host. We need to consider what this is doing. And we also need to consider what the various software levels are doing. Like, you have a new version of KVM, which has gained some new cool features, and suddenly everything looks different in the host, which is also, yeah, features added is mostly not that bad, but features removal, if you migrate to a different version, is probably not something we want. And also, we don't want to present users with too much required choice. Basically, we want to wait to for them to tell, hey, I want a reasonable CPU which runs on this generation and is just reasonably well matching whatever my current host is doing, and just give it to me and don't bother me with any details. And the other thing is, of course, of the configuring that libvirt needs to be able to figure out what can we actually tell QEMU to configure. And of course, these are not the only open questions. These are just some open questions. And I could probably have added some more slides with open questions, and you will be probably telling me more open questions. It's basically, how flexible do we want this to be? Do we want to have really weird Frankenmonster CPUs that can be anything weird, which will never exist in the wild, like combining wildly different architecture levels and stuff like that? Or do we just want to say, okay, you want this, but this is too crazy, don't do that? Then also, what level of compatibility do we want between different systems? Do we want something like just, oh, there might be some minor difference between those two hosts and we want to migrate it, so we just need to be able to configure some slight differences and then we can just seamlessly migrate it, which looks way more doable than I have here this Graviton and I want to migrate to this Ampere, which is just insane probably. And also, what do we actually want to expose? Can something be hidden? Can we be a bit closing over things because in reality it doesn't matter, and implementing it would be much more trouble than it would be actually worth in the end? That's another question. So now that we have so many open questions, I guess many people in here also have more open questions and comments, and because I also already saw people smiling, nodding, so maybe let's open it for questions now.
So the errata issue is something that we put a lot of thought in with managing ARM machines in GCE, and I think the one unfortunate reality is no matter what you do, the guest is painfully aware of whatever misfeatures exist on that system. So I think maybe one way to go about it wouldn't be to hide that detail from them, and in fact, report to the guest what your schedule, the pool of machines is that you support. Like that might be one way around it, but to say that a certain implementation behaves exactly the same on another system is seemingly playing with fire. Yeah.
There is a problem with the errata. Like I don't know anything about ARM, but I spent like 10 years thinking about features on x86. So there are some lessons learned. The problem with the errata is that you don't know that they exist until they are discovered. So basically they are, you can have a bit, but it doesn't tell you what works. It tells you what doesn't work. And all the machines that you have running until that point, you cannot teach them about the new errata because they don't have the kernel, the new kernel, or they don't, even worse, maybe they have the kernel that knows about the errata, but it doesn't have the bit because it was started without. I don't know if ARM has features that were removed and they added a bit to tell you that the feature is not there anymore. God, I mean, how how do you know that it that it might disappear in the future? So errata is basically a negative feature. There's no hope of fixing it.
Yeah, negative features are just nightmare, I guess.
Even worse than
And the problem there, though, is like it's not even described in the feature registers that actually describe the architectural feature set of the system. It's mostly discovered based off of the MIDR of the system.
So we do have negative features. So you know a bit of but it's worse than that because there's a you can basically do anything you want with the architecture as long as you pay some money. And for example, you can have a PMU of some revision, but you can also have an implementation-defined PMU, which doesn't follow any of the rules that are contained in the architecture. And the way you indicate it is by having something that says, it's not that I don't have a PMU, I have a negative PMU. It's actually a signed value. It says -1. It says, no way, I don't have that. I mean, I have something that you can't make use of. So we have this spectrum of not only of revisions of particular feature, but also sometimes something that becomes negative. Tell you, no, actually it's gone. So obviously you can't. I mean, these two implementations are not compatible. If you want to migrate between these two, too bad, you've lost. So I've worked on some vague idea where, because the architecture gives you a way to specify a synthetic MIDR that says this is a software implementation of a CPU. And what I came up with is not very good, but that's what I have at the moment, which is basically, I tell you this: you have a software revision of the of a CPU, and here's a firmware call that will describe all the possible revisions of implementations you can run on. Go and implement all the workarounds you can, and if you have conflicting workarounds, tough luck. You can't run. But it's I mean, nothing's perfect there. It's basically broken by design, by flexibility, and if you think ARM is bad, think what RISC-V will be 5 years from now, because that will be even worse.
So should we basically consider, hey, we have some kind of QEMU CPUs, which are like the real CPUs, but just close enough?
So the one thing that I kind of worry about is, so I guess my background, I come from the Google Cloud side, so don't really expect a lot of influence over the guest kernel and anything. And these sort of like KVM specific or QEMU specific like PV interfaces are kind of terrifying to me, because it doesn't mean anything for the customers that are unaware of it. So I think if we were to go in a direction like that, we might want to get something architected for it.
Yeah, it would need to be architected. We can't just define our own. I mean, I have a prototype, it's nice, it's fancy, but on its own, it means nothing. It has to be architected, it has to be supported in actual revision of some VM firmware, and it has to be universally adopted. So it means that Hyper-V should also, for example, be able to expose these things.
Don't just say yes or no. Tell me how naive it is. Has anybody tried talking to Microsoft about this?
Not personally. I don't have any direct contact with them. But I think that's why we have ARM. I mean, that's their job, really. I mean, we can ask them to yeah. Well, it's I think it's more than just individual companies. I think it's as a community. If we want ARM VMs to be in a better shape when it comes to live migration across implementations, then we need something that is consistent, and the right place to define that is at the architecture level. So that's, for me, that falls directly onto ARM's plate. They do. It's not the first time I mentioned these sort of things.
So one more question for me that I just thought of. Do we have any lessons learned from other architecture CPU models where you say, whatever you do, ARM, don't do that, just never do that? Any good advice there?
Well, negative features like behave as if they don't exist. Like, don't even bother exposing them to the guests. So the kernel has to do something sensible. Like, tell the guests that every old obsolete feature exists, because if it's obsolete, nobody's using it anyway.
I guess just a little bit of a news update, since you had mentioned it earlier. The KVM series that you were talking about to allow configurable ID registers was merged an hour ago. So, but I think Mark had a really good suggestion on how to improve it for user space too.
Yes, So from what I understood, you want to have some sort of interface that tells you not only what the host supports, but also what are the bits that can be modified.
Exactly.
Yeah, so I think we can probably help with that. So the way with that patch series, you've seen the way the ID registers are managed. So they are mostly read-only at the moment, even if we allow people to write to them. But because they are segmented in fields, we track internally which fields are actually writable. So one possibility would be to expose the masks that describe which fields are writable to user space, so that you could discover that, and there would be, each mask would be associated with one field in an ID register, and that gives you the features that would be available to modify.
So I think with that, the default value in KVM for all these fields would describe it at the maximally supported feature set. So effectively, it would become a mask of features that user space could negate, actually. Or downgrade, yeah.
So you may have just answered it. Yeah, so does every feature that's advertised in the ID register come with a corresponding knob that the hypervisor can turn off to disable it? But having a writable feature bit implies that the hypervisor can do something about it.
I can move as well. So it means that the hypervisor can do something about the value. It doesn't necessarily mean you can disable it. There are some features where the architecture mandates that it's there, but you have various level of support. So we could say, okay, you can't turn it off, but you could go back to the basic level of support. Or at least we don't advertise it. For some features, we just can't disable them, but we can stop advertising them.
That's not too far off from the x86 model too, though, right? It's like a lot of like the user space visible features. There's no controls to turn it off in VMX, nor is there for EL2 on ARM. It's kind of on the good intentions of the guest that it doesn't actually use a lot of those user space visible features.
It's not necessarily written anywhere that an undefined DOP code actually raises an exception. Sometimes it can just do what it's supposed to do in later releases.
The architecture is pretty precise in this department, and it says that it will most often result in an undefined. it will undefined.
There's a certain probability that you're running bare metal or in a virtual machine. Most often you're running on bare metal, it does an exception. If you happen to be running on a virtual machine, maybe it doesn't. No, apart from that, one suggestion is do not just think of what the API looks like, think of what the documentation looks like, because these things are a nightmare to document. So make sure that you also teach the VMMs what to do with your API.
So if we were going down that road, my plan would be to report something that has exactly the same format as the ID register, at which point I point you to the ARM and say, that's what it is. So I'm convinced that if you want to specify the shape of a vCPU, you will eventually have to specify all these 56 ID registers, all of them. I don't see another way.
I think that the KVM documentation starts and ends with how the ID register interface interacts with our existing feature configuration model. Like we have like the feature flags. I think that would be really important to document because it does have weird quirks about it. But otherwise, in terms of what's strictly described by the architecture, I think it's best that we just give it to the ARM. Well, I think that's the question too.
Just an example for x86, we have some bits that we later realize they don't depend on the hypervisor. User space can always set them. but maybe if you have an older hypervisor, it's not set. So some bits the user space knows it can always set. Some bits you can always set if you have a certain capability. Some bits you can always set if you enable a capability. So it's not just that you have a documentation of what the bits in IDR do. It's basically how the features interact with other parts of the hypervisor. So these are kind of quirky things that are going to happen.
Yeah, so I think what we also need, Alex, you're. sorry, I don't. Sorry. Sorry, I didn't. Yeah. So I think what we also need to consider is that libvirt is. I think they are really hot on you get what you define, and if you say the same, you want the same thing, you get the same thing. So if something can change, we probably need to expose it to libvirt so they can configure it and build whatever they need on Flex and so on.